Today I want to talk to you about something that's known as a vector field. So let's consider a 2D vector field. Suppose you have an XY axis, and what we can do is to every point in space here, we can assign a vector field. Now, common notation, vector fields usually have a capital F. You indicate the parameters, which in this case are going to be X and Y. And then usually they're of the form like some function h of x comma y times I plus g of x comma y times j. And so let's take a look at an example. Very basic one. So let's let f of x comma y equal the vector field negative y times I plus x times j. Okay, so what this means is to every point we can assign a vector. So let's say we're going to start over here, and this is going to be the point 1, 1. So 1, 2, 1, 2, 1, 2, 1, 2. We'll see if we need more points. So at the point 1, 1, if we were to do f of 1, 1, we would get, it says negative y, so the y component here is 1, so we'd have negative 1i plus x, but x is just 1 here, so it would be 1j. So that you can write if you want negative 1 comma 1 with the little vector brackets. Negative 1, 1 would go back 1 in the x direction, forward, up 1 in the y direction. So you'd have a vector that does this, points like that. Okay, and so what you could do now is for every point in space, find a vector. So let's go over here. Let's say you went here. You would, this is the point 2, 1. And so if we did f of 2, 1, we would get negative y, which would be negative 1i plus 2j. So that's 2j or xj. And that one looks like this, up 1 over 2. So you've got a vector that looks like this. There's some other interesting vectors, maybe the one that's right here. So that would be f of 2, 0 would be negative 0 or 0i plus 2j. So you have a vector that goes straight up like that. And let's do one more. Let's suppose you were going to look at the point right here. Let's use a different color. Let's use red again. So this is the point 0, 1. If we did f of 0, 1, we would get, well, you get negative y, so it would be negative 1i plus 0j. So that would just go, if we're careful, it's going to go negative 1 in the x direction and not move in the y direction. So that vector is going to look like that. This is the vector negative 1, 0. So you can see you get every point in space would have a whole bunch of vectors, have vectors associated with them. And so if you took the time to do all of this, here's what you would get. There it is. Now there's lots more points I could pick and draw a lot more vectors, but this is a good set of points. It seems like these arrows, these little vectors, are pointing us around in some kind of circle that maybe would go around like this somehow, like we're specifying a path some way. It turns out that's not a coincidence in this case. So let's think about this particular problem we were just looking at. We had the vector field f of x comma y equals negative y I plus xj. So to sort of justify that these things are giving us a circle, I want you to consider another vector. I don't know what we'll call it vector m. And vector m is x times I plus y times j. And if you look at this vector is a very special name. It's called a position vector. because all it does is it goes from the origin out to a location. And how do you know that? Well, because the x component of the vector is just x and the y component of the vector is just y. So that's why this thing's a position vector. So that's pretty handy, actually. Um, so what can we do then? If we compare, for example, um, this vector here and this vector here, there's actually something pretty special about them. So if I do f of x comma y, and I go dot product with vector m, then you end up getting, remember how to do dot product, you multiply the x components together, multiply the y components together, and add them. So if you do that here, you will get negative yx plus xy, which is 0, which means it means that f of x comma y is perpendicular to m. That's something we proved before, that if you have a dot product of two vectors to be 0, then the vectors themselves are perpendicular. So that means there's little right angles here. Um, but that turns out to be a property that circles have, that is that their tangent vectors are always perpendicular to the radius. So if I draw a bunch of radii in here, every one of these radii will be perpendicular to these tangent vectors that we've drawn. And what's interesting is if you check all these things here have length square root of x squared plus y squared, because that's how you get the length of a vector. So this is like the, you see, this is the length of vector m. But we know that that is equal to some kind of constant, which is the radius squared. So this is your first little introduction to what a vector field is. All it is simply you have a space in the plane, and you were, or it could be in 3 space actually too, and we're just saying that every point in space has a vector associated with it. Good real life examples of vector fields. You could be walking outside on a windy day, and you might notice sometimes the wind pushes on you harder, and then you walk a little further down the road, and maybe there's trees and stuff blocking the wind, and then you don't have any wind pushing on you anymore. So in that case, the vector field goes to 0. So maybe here's something. Here's a bunch of vectors, and the longer vectors mean the wind is blowing more strongly. A shorter vector means not necessarily. So we could have a bunch of vectors like this, and who knows, maybe over here they're blowing that way. So if I decide to go for a walk, I might go through a walk through this vector field. Maybe I'll follow this green path and I'll put little arrows on it, and I walk around in some curved fashion, and maybe I come around like that. So this is my direction of movement. So this is my curve. I'll call it C, and this is where I started. The whole curve's where it started. So you'll notice, like for example, at this first point, I'm going to put a little blue dot. The vector field, the red vector, is sort of heading in the same direction that I'm heading in, right? Because I'm moving along like in that direction. But as I get over to here, I'll notice, like say I go to, let's go use different purple point, then the path I'm heading along, I'm heading in this general direction, but the wind is actually blowing the opposite direction. So we've all had this happen where we're trying to ride our bike on a windy day or run, and the wind is blowing in our faces. So the blue point is a point where the vector field, I'm getting some help from the vector field. And the purple point is a point where the vector field is, I don't know, I'm going to use the word hurting me, right? It's not helping. It's working against me. It's not helping at all. So it turns out this concept of getting help or being hurt by a vector field as I try and move through it is extremely important, and has some really cool theorems that come up as a result. Okay. Thanks for watching. See you then.